Yes, question number 130. Which of the following is not correct? Right. So before we go into that question, let's look at some equations here. What is the equation for drag, parasitic drag?
Coefficient of drag into half rho square.
Yeah. All right. So yes. And what is Q here?
Half rho
The
square.
dynamic pressure, which is half into density times V square. So all these discussions you can see, we don't really play around with the density as such. Unless you climb or descend, we assume density to be constant, which is not always the case, but theoretically we keep it like that. And what is V here? V is the CAS.
True airspeed.
True airspeed. Alright, now we saw the dependency of the lift induced drag. So the measure of lift induced drag is the lift induced drag coefficient, but that depends upon coefficient of lift. What to what power? Square. So it's square of coefficient of lift and it's inversely proportional to the aspect ratio. Right? So it's inversely proportional to aspect ratio and directly proportional to square of the lift coefficient. Alright, now imagine that I double the velocity. So velocity is doubled. So velocity double means the true airspeed is kind of doubled, right? So V becomes 2V. What is the immediate change? What is it affecting? It's going to immediately affect your dynamic pressure, right? What happens to dynamic pressure?
4 times.
It increases 4 times because Q is proportional to square of velocity, not velocity. So velocity is doubled, therefore Q increases 4 times. 4 times Q. If I so what happens? What have I done here? I have increased the velocity. So if I want to maintain lift, when I touch the velocity, what should I do?
Angle of attack.
You have to now change the angle of attack. So since I have increased the velocity, yes, what should I do with the angle of attack?
1 by 4 times.
The angle of attack has to be
Should be increased, right?
increased. Angle of attack should be decreased.
Oh,
Yeah, because as speed increases, angle of attack
inversely
reduces.
proportional.
So as speed increases, angle of attack
Reduce.
reduces
So you are asking?
to maintain lift. Yeah, so as speed is doubled, angle of attack reduces. Now where does that 1 by 4 come? Learning. You have to reduce angle of attack in such a way
4 times.
that it has to be reduced in such a way that your coefficient of lift
Basically
reduces.
balances out the change in dynamic pressure.
That's it. So coefficient of lift has to be reduced to 1 by 4. How is it possible?
Yeah.
By reducing the angle of attack. It's not that angle of attack is reduced to 1 by 4. No. The angle of attack is reduced in such a way that the coefficient of lift reduces to 1 by 4 times of the previous value. We have seen this before. So when you reduce the coefficient of lift by 1 by 4, you compensate for increasing the dynamic pressure by 4 times. This 4 and this 4 is going to get cancelled, so you have the lift maintained. Is that clear? We have seen that earlier. So if you are confused, just put this in the equation again. The lift equation, lift is equal to coefficient of lift times half rho V square times S. So what happened to rho here? Half rho. So not rho, what happened to V? We have doubled the V, so V becomes 2V square, and 2V square is 4V the whole 4V square, 2V the whole square, that is 4V square. So since if I don't do anything about it, you can see lift now increased by 4 times. So to now bring back the lift to the normal value, we have to reduce your coefficient of lift by 4. And how is this possible? Coefficient of lift depends upon camber as well as angle of attack. You have to play with either of those. The best thing is to reduce the angle of attack because when you fly faster, you probably might not be able to increase your camber by flaps and stuff. So reduce your angle of attack in such a way that your coefficient of lift reduces to 1 by 4's previous value, and thereby the lift is maintained. Is it clear? We have seen this before. Yes? Alright. Now, when you reduce your coefficient of lift by 1 by 4, what is the meaning of that? What have you done here? Physical meaning. You have reduced the ability of the wing to produce lift. But the wing is going to produce the same amount of lift because now you have increased the speed. So the lift is not going to reduce, but the ability of the wing itself to produce a lift has been reduced to 1 by 4. What will this do to the induced drag?
So it will also reduce.
Reduce. So see, it is not really talking about the total lift. Total lift is different, and the capacity of the wing to produce lift is different. The wing's capability to produce lift has been reduced, but the effective lift is going to be the same because now the wing is flying faster, double the speed. So this production of same lift is not because of the capability of the wing, it is because the wing is made to fly faster. The capability of the wing, you have reduced it to 1 by 4, and therefore the lift induced drag is also going to reduce. Reduce by how much? You see what the dependency of lift induced drag on the lift coefficient? CDI is proportional to CL square. So what is the lift induced drag? What is going to happen? That is proportional to CL square. What happened to CL here? You have reduced CL by 1 by 4. Therefore, this is CL square by 16. So when you reduce your coefficient of lift, the ability of the wing to produce lift by 1 by 4 times, you have automatically reduced the induced drag by 1 by 16 times. Alright? Yes. Now, the drag equation, drag is equal to CD times Q times S. What is CD? What happened to CD here? CD becomes...
So it is reducing, right?
Yeah, the drag reduces because the induced drag is reducing, total drag is going to reduce, right? So what happened to CD? CD was initially proportional to CL square only. Now it's proportional to CL square by 16. Therefore, the CD coefficient of drag reduced by how many times? 1 by 16 times. Yes. So 1 by 16 times CD. What happened to Q?
You are increasing the Q, right?
Yeah, when you double the velocity, Q increased by 4 times. Right? So Q 4 times into S. Therefore, what happens here?
1 by 4 times.
QS. CD
So where
QS
the CL
is
have a 4 will go
Say again?
in this question? So where the CL by 4 square we use in the equation?
No, this is the equation for drag. CD Q into S. What is the CD? Now, coefficient of drag, what happened to that? It reduced by 1 by 16 times. So coefficient of drag reduced by 1 by 16 times. Dynamic
No, sir,
pressure.
how your 1 by 16 came, sir? 1 by 16?
So coefficient of drag, induced drag is proportional to square of the lift coefficient. Lift,
Okay.
what happened to lift coefficient? You have to reduce lift coefficient by 1 by 4 times.
Okay.
Therefore, what happens to induced drag? Induced drag is going to reduce by CL by 4 the whole square, which is CL by 16, 1 by 16 times.
Okay.
Right? Yes. Now CD reduced 1 by 16 times from the previous value. Q has increased by 4 times the previous value because you have doubled the velocity here. Therefore, effectively, what happens to total drag? Total drag reduces by, the lift induced drag reduces by 1 by 4 times. Understood? So CD QS is nothing but the previous drag which you had. Now it is divided by 4, which means the drag kind of reduced by 1 by 4 times. Is it clear? Right? If this is not very clear to you, let's look at the very opposite of this. Probably that should actually help you, but just go through this very quickly. Write it down and tell me if you haven't understood. Alright, so in this case, let's look at reducing the velocity v to half. What happens to your dynamic pressure? Will be reduced by 1 by 4 times. Right? Now, to maintain lift, what are you supposed to do? You have to increase your angle of attack because you reduce your velocity, the angle of attack has to be reduced. The same figure here. As you reduce your velocity, your angle of attack has to be increased. Yes, increase in such a way that your CL increases to
4 times.
4 times your previous CL, so that the net lift produced is going to be the same. Remember, the total lift produced is the same, but the capability of the wing to produce the lift has increased. But that is not going to increase the total lift. because you have equally reduced your velocity, so it compensates. Right? Therefore, since CL increases to 4 times CL and coefficient of induced drag is proportional to square of CL, the coefficient of induced drag is proportional to square of CL. CL is now 4 times CL, the whole squared. Therefore, that is equal to 16 times CL squared. So the coefficient of induced drag has increased by 16 times. So here also you can see this is equal to CDI, coefficient of induced drag, by 16. Now coming to the induced drag equation, it is coefficient of induced drag times Q times S. So coefficient of induced drag has increased by 16 times. What happened to Q? Q has reduced by 4 times.
1 by.
Yeah, so it's 1 by 4, yes, into S. So that is 4 times
Okay.
coefficient of induced drag times Q times S. 4 times coefficient of induced drag QS is the induced drag dI. So what happened to the induced drag? Induced drag increased 4 times when you reduce the velocity. We have seen this before, that as you reduce your velocity, the induced drag is going to increase. As you increase your velocity, induced drag is going to reduce. So this is the mathematical proof of the same statement. So again, we have the graphical representation of this, which we have studied before. The graph between coefficient of induced drag and angle of attack. So, and indicated airspeed. So at lower speeds, you can see as the speed is lesser, you have higher coefficient of induced drag. As you go higher on the speed, the lift induced drag reduces. So you can see all these things are pointing towards the same concept, that as you increase the speed, lift induced drag reduces. That's because the vortices now get lesser time to kind of complete circulation and the lift induced drag reduces. Did you understand the same concept being explained in different ways? One using the normal concept, mathematics, and this is the graph. It's all the same. Yes, Anuj, understood?
Yes, sir, got it. Yes, no.